Okay, this video is on chapter 2.4, finding the heat of combustion or the change in enthalpy using the specific heat capacity of water as a way of trapping the energy. So we'll look at this equation. Q stands for the energy, and in your data booklet this is written around the other way. So that's the mass of the water, that's the heat's being trapped in. Specific heat capacity of water and the change in temperature of the water. So we're using trapping the heat in water to work out the amount of energy that's being released from a combustion reaction. The heat of combustion can be a vague term, or the molar enthalpy, so the energy for 1 mole of a fuel. So we'll be looking at how many kilojoules for every mole of fuel, or how many kilojoules for every gram. And we can turn that into the change in enthalpy for a balanced reaction. Okay, so just remember, mass is for the mass of water, and the change in temperature is the difference between your initial temperature and your final. So heat of combustion versus change in heat. Heat of combustion is kind of a bit of a vague term. It means how much energy, but how much energy for what type of unit will depend on the question, really. So how much energy is released if you have 1 mole? All of these can be written underneath here, and they're referring to 1 mole. So how many kilojoules of energy would you produce if you combusted 1 mole of some sort of fuel? Or how much kilojoules would you produce if you combusted 1 gram or 1 litre? So they're the heat of combustion. Change in enthalpy is for the number of mole. It's generally 1 mole, but if the balanced equation is more, then it's for however much on the balanced equation. Okay, so we're using this setup. Our fuel is in here that we're combusting, the energy is being released, and then it's being trapped in the water. So what we have to measure, the temperature of the water increases, so the change is we're going to have to measure the initial temperature, and after the reaction's finished, after you've heated it, the final temperature that it gets to, and you convert that to joules using this equation. So this equation, the units are in joules, so you need to remember that. So you would need to convert that to kilojoules. It's obvious that it's in joules because the specific heat capacity is joules. C is 4.18 joules per gram per degree. So we're putting our fuel in here. We're going to weigh it to start with, then do the reaction burn, some of it, and then because you're turning the fuel into carbon dioxide and water, they are gases, so they'll leave that, so this will weigh less. So we weigh the mass, this should be around the other way, the final mass minus, no, the initial mass is higher, it is around the right way. Initial mass minus the final mass will give you the mass of fuel that you lost. So we're doing this at the beginning with fuels, but you can see that it's a bad way really of measuring the heat, because you're losing a lot of your heat out to the sides, and you're also losing heat because the container itself will absorb some heat. So clearly the amount of energy that you end up trapping is going to be a lot less than the amount of energy that is actually produced. So a better way of doing it, a more valid method, is if you do your reaction inside a container and the water is surrounding it. So we'll look at this at the end of the year when we're measuring the heat of combustion of food, and so we put this in a thing called a bomb calorimeter. So why don't we just put a thermometer over the flame? Because we would be losing heat and the thermometer would increase too quickly, so it's not really stretching out the result over a large amount of fuel. So yeah, and if you trapped the heat, heated a container of air, then the air would expand and increase in pressure, and then the container would break. So that would be really dangerous. So you can, water will absorb a lot of heat, has a high heat capacity, and it's safe. So if you don't boil the water, then you're trapping a lot of energy in safely. So our equation, basically you don't really need an equation, that you can build this from the units on the specific heat capacity of water. You need 4.18 joules for every single gram going up every single degree. So 1 gram of water will go up 1 degree if you put 4.18 joules in it. So if you have 2 grams of water, then you would need twice as much. So you can see if you multiplied that by 2 grams, then these units would cancel out the grams. Or if you had 1 gram of water and you wanted it to go up 2 degrees, then you would need to multiply it by 2 as well, because you'd need twice as much for it to go up 2 degrees. So that would cancel out too. So basically, these units here, because you've got grams and degrees on the bottom, you realise that in order to cancel them out and be left with just joules, you would have to put grams and degrees on the top. And what's left after you've cancelled out the grams and degrees is joules. So your answer is going to be in joules. Remember this here, it's the change. So the difference between the temperature that you started with and then it's heated and the temperature goes up, that amount that it goes up is the change. So you need the final temperature and the initial temperature, and you want the difference between them. Okay, so the question in your textbook, just a bit of practice, nothing to do with the fuel, it's just working out how much energy has gone into the water. So you need to know the mass of water in grams, and 1 ml of water weighs 1 gram. So if you've got 500 mils of water, then you have 500 grams. So if we just put our numbers in, you've got 500 grams of water. It hasn't given you an initial and a final, it's actually given you the change, that it's gone up by 15 degrees. So if you just multiply those, cancel them out, and you'll get a 3.14 by 10 to the 4, so 31,400 joules. I have to check if you've totally answered the question. So the question has asked, calculate the heat energy in kilojoules, which is a classic exam thing. They never get you to quote. You work out your answer, you think you're finished, and then you look at the question and you see that there's something else you have to do. So you have to get used to, once you got your answer, look back, make sure that you've actually answered the question totally, because there's always something else. So you're dividing it by 1,000 to turn joules into kilojoules, because kilojoules are a larger unit. Dividing it by 1,000 is the same thing as multiplying it by 10 to the minus 3. So if you multiply two indices, you add the indices. So 4 plus minus 3 will be 1. So you've got 10 to the power of 1. 10 times 3 is 31. Okay. Would a spirit burner be a valid method? No, we've already said that you lose the heat, so you can't. It's not accurate, it doesn't get close to the real answer, and it's not precise because you can't repeat it, because you would lose heat. If this was a little bit higher, it's really hard to control the variables. Would a spirit burner be a valid method to compare? So if you don't want to know the actual answer, the accurate answer, the real amount of kilojoules. If you just want to compare two fuels, as long as you set up the technique exactly the same, so that they're losing the same percentage of heat, then you could compare the two fuels and see which had it would be a more valid method to compare two fuels than to find the actual heat of combustion. So find the heat of combustion, or the molar enthalpy, so the enthalpy, the energy for 1 mole. To do that, we need to put some water in, so you want to know how many grams of water so you can accurately measure out the volume. Put it in a container, convert that to mass, so you've got 100 grams. You measure its temperature initially, and you measure the mass of your spirit burner. Then you light it and heat it continuously until it goes up about 40 degrees. Don't go any more than 40, don't go over 80, because it won't be a linear relationship between the heat energy you've added and the temperature rise that's going up. So you can't use the temperature rise as an indication of kilojoules accurately anymore. It's not that you can anyway, but so you let it go, and you want to find the change. So you'll have to put the flame out with a little cap. Let it heat, let it go for a little while, because the temperature might keep increasing, because some of the heat energy, the last bit that you've added, will slowly make its way up to the thermometer. So just wait for a little while, make sure that you've got the final temperature rise, and then you can work out the difference, how much the temperature went up. You reweigh your spirit burner to find out what weight's left, take it away from what you had to start with, and you can work out how much fuel is being produced. So you're doing two things. In order to get kilojoules per mole of fuel, you need to work out the kilojoules from the water using Q equals MC squared, MC to the change in T. Sorry. So kilojoules from here, and then per mole, you need to work out the grams of fuel that you burnt and turn that into moles. So you've got two things, and then you put them together to find kilojoules per mole. Okay, so that's basically, work this out from the water, Q equals MC change in T, and reweigh your spirit burner and work out the grams of fuel that burnt, turn that grams into moles, and then you divide one by the other and you'll get kilojoules, how many kilojoules for 1 mole. Okay, so this is example 2.42. So we've got some fuel, methanol. They've actually given you the mass of fuel. They haven't given you the initial and final mass, so that you have to work that out. They've given you the answer, the amount of fuel that's been burnt. So this is, you'll have to turn this into moles. If you're asked to find the kilojoules per mole, you need to turn the mass into moles. The heat, after you've burnt that, has gone into the 100 mils of water. So you need to make that grams, 100 grams of water, and the temperature's gone up from this to this, so you need to work out the temperature rise. So to get the energy in the water, you've got Q equals MC change in T, so your mass, your change in T is 17.41 degrees, it's gone up, and your water, you had 100 mils, so you've got 100 grams of water, and it's 4.18 joules for every gram for every degree. So if you just multiply those, they'll cancel out and you'll be left with joules. So you've got 7,277 joules, but the question's asking for kilojoules, so you'll need to turn that into kilojoules divided by 1,000. So now you've got your kilojoules, you need the moles, so you need to turn this into moles. Significant figures, we've got 3 here and 4 there and 3 here, so you'll need to cut that down to 3. Okay, so you've got how many grams of fuel. Work out the molar mass of methanol, and then you get 0.0111 mole. So to work out how many kilojoules for 1 mole, your ratio, you know that you have 7.277 kilojoules for that many moles. You can see that you kind of don't need to do a ratio. If you want to have it per 1 whatever, when you divide the kilojoules by however many moles, your answer will be how many kilojoules for 1 mole because of the ratio. So if you take that over, it'll cancel out. So 656 kilojoules for 1 mole. If you're asked to find the change in enthalpy, you have to actually write it out like that. So even though over here you've got the amount of energy, because you've been asked to do this, you have to write it out like that. So you have to write the fact that it's exothermic, has a negative symbol, and you have to put in the kilojoules per mole, and you'll get 1 mark for those having those things often, 1 mark for the correct answer, and 1 mark for the correct number of significant figures. Okay, so if you're doing a thermochemical equation for the combustion of methanol, you'd have to write out the combustion reaction, and you have to add the change in enthalpy. So the thing is, this combustion reaction has 2 moles, and you've worked out your amount of kilojoules for 1 mole. So you just need to multiply it by 2. Could have just multiplied the other one by 2 rather than going right back to the beginning, but anyway. So that's your 656, I think it was, doubled. So when you write the whole thermochemical equation, you have to include it for the 2 moles. How would you work out the heat of combustion for kilojoules per gram? You don't have to turn the grams into moles. You can just use them as they are, and you get how many kilojoules for each gram. So just divide it like you just did before. How many kilojoules for 1 gram? Take the 1 over there, they cancel out, etc., etc. I should have written a 1 here. Okay, so that was our prac. So, as well, when we look at, I'll go back. Look at, where's the equation? We're back there. Look at the equation. So far we've been finding the energy. But this is a constant. And there's 3 other things in the equation. So you could be given, if you're given 2 of them, you could be asked to work out the 3rd one. So that next question we're looking at is you're asked the final temperature. So you need to rearrange this equation to find out the change in temp first. And then once you've got the change in temp, you've got this. If you're given the initial temperature, you can find out the final temperature. So let's do that question. Final temp. 7.8 kilojoules of energy. So they've given you the energy. Was absorbed by 750 mils of water at 22 degrees. How much would it have gone up? So can you see the trick here to start with? The Q equals MC delta T. The Q has to be in joules. So turn the kilojoules into joules first. Multiply by 1,000. And this obviously has to be in grams, the same thing. So you rearrange your equation. Oh, have I been lazy here? I have. That's not very good. Alright, so these are multiplied on this side, so we take them over the other side. You can multiply them together, take them over the other side and divide them. So it'd be 7,800 divided by 4.18 multiplied by 750. So when you do that, you find that it's 2.5, the change, which means you started with 22 degrees and then it went up 2.5 degrees. So it's gone up to 24.5. So rearranging that equation, let's subtract it on this side, take it over the other side and add it. Okay.